it is little different from 8088. 8088 is very easy. Why 8088 is very easy? Because the memory also has 8-bit data bus, microprocessor also has 8-bit data bus. Direct interfacing is possible. Right? You just have to see the address decoding part. Right? The procedure which I have explained you, once again you have a look into this. Okay? And then also go to the video again and again for better understanding. Fine? Okay. So now today in this class we will learn how to interface a memory to 8086 microprocessor. Okay? To 8086 microprocessor or 80286 microprocessor. Can you tell me what is the difference between 8086 and 80286 microprocessor? Can you tell me what is the difference between 8086 and 80286 microprocessor? Can somebody tell me about this? No. Tell me in terms of address bus. What is the address bus size in 8086? 20, right? What is the address bus size in 80286? Come on. What is the address bus size in 80286? 40. Whatever something came into my mind, your mind, huh? It's not my idea. 24-bit address bus. This has got 20-bit address line. This has got how many? 24-bit address line. This has got 16-bit data bus. This also has 16-bit data bus. Remember this. Do not forget this. Never forget this. Okay? Now let us see how do we design a memory system for this. You know basic technique of interfacing memory to 8088 processing. I'm not going to repeat anything of that now. You are supposed to know it. I have shared you the videos also. I have shared you the contents and you are supposed to know about it. Have you understood this? Okay, that's very important. Okay. And few basic things also you're supposed to know. Right? Few basic things also you're supposed to know. What are those basic things? 8086 has 20-bit address bus. 80286 has 24-bit address bus. Okay? Now, can you tell me how much memory 8086 microprocessor can address? 1 megabyte. How much memory? Your 80286 can interface? 16. How does 16 MB came? 2 to the power of 24. Okay? 2 to the power of 24. Okay? Okay, so you can see that, see, an instruction like this, it can put a 16-bit content into a address 437AH. Okay, what this move within the square bracket 437AH BX does, a 16-bit content has been put into the how many bit address? This is the offset address, right? Okay. Okay. So now, how does the word is written? Suppose, let us consider that you are trying to transfer a 16-bit content to an address 437AH. Okay. How does it store this 16-bit content? Listen carefully. You are here to learn, right? If somebody is there only for attendance, just I take the attendance and go out of this class. If you are ready to concentrate, That's well and good. Somebody is coming only for attendance, just give attendance and go. Not a problem, I don't mind. But when you're in the class, listen, concentrate. It is very important for you. I don't want to tell this every time to you all. Concentrate into this. These are something which is very much important for you. Most of it doesn't know about it. Right? Look at the instruction. Move within the bracket 437AH, BX. What it does? Tell me. I want answer from you. It moves how much content? 16-bit content to an offset address 437B. Right? 16-bit content means you have a lower half part and upper half part, right? Your BX register is having BH and BL. This is 8-bit, this is another 8-bit. That means 1 byte, this is 1 byte. Can one location store entire 16-bit? No, right? One location cannot store it. So tell me what will be stored in 437A. It requires two addresses, right? Two addresses. So that means it requires 437A and 437B. Can you tell me what will be stored in 437A and what will be stored in 437B? So here what you stored is content of BL. Here what is stored is content of BH. Totally it is BX. Have you understood this? That means whenever you try to write a 16-bit data into memory, try to understand this. Whenever you try to write a 16-bit data into memory, it is writing in how many locations? Two locations, yes or no? Right? At a time, it cannot write in one location of the memory because memory is byte addressable. One location in the memory can take only 1 byte. So whenever microprocessor writing data into the memory, it will take 2 locations. Yes or no? And those 2 locations are taken from different memory devices. Just try to remember this. That's where I spoke about the mismatch between a single memory and an 8086 microprocessor. Try to understand this concept. 8086 has to read or write 16-bit data, but one memory chip has got only 8-bit data, right? So how do you read 16-bit data from the memory? It uses 2 locations from 2 different memory devices. That is the way you interface a memory system to 8086 microprocessor. This problem is not there in 8088, right? You never have this problem, right? It is direct, right? But here, system is little different, right? Be careful with knowing about this. See, to complete one write in one cycle, in the memory has to be set up into 2 banks. Here, entire memory will be divided into 2 banks, right? This particular memory address belongs to one bank. This particular memory belongs to another bank, right? So there will be 2 memory devices. See, try to understand this. There will be 2 memory locations, 2 memory devices. This memory can give you only 8-bit data. This memory can give another 8-bit data, right? So now here in this case there is 16-bit, right? So how does it write the 16-bit data? So we are going to design a memory in such a way that this memory device will hold 437A. So this memory device will hold 437B. So microprocessor wants to write it in the memory, right? When microprocessor wants to write it to the memory, what microprocessor will do? The memory is designed in such a way that 437A will be available in this memory device, 437B will be available in this memory device. So it will try to store BL here and it will try to store BH here. Have you understood now? Have you got little bit idea how does 8086 reads and write this? So address map, now see here. Now let us talk about address map. See, when you take about address map of this memory device, this both the memory will have a continuous address map, right? But all even addresses will come in one of the memory devices or odd addresses will be coming in the other memory devices. Have you understood now? Right. So we divide the memory in such a way. Try to understand this before going into the actual topic. I'm just going to explain you how do we arrange the memory. Right. Assume that your 8086 microprocessor can address how many memory locations? 1 megabyte locations, right? 1 megabyte locations, right? So for 8086, interfacing one memory chip, try to understand each and every point which I am telling here. For 8086 microprocessor, interfacing one memory chip, one memory chip of 1 megabyte will be impossible, right? Why? Can I interface one memory chip of size 1 megabyte to 8086? It's not possible, right? Why it's not possible? Because all are 8-byte addressable, right? All are byte addressable. My all entire address range from 000H 0H to F available in one device. I cannot extract 16-bit data from here, right? Can I extract 16-bit data? I can, right? Try to understand. This is one memory chip. Starting size 1 megabyte. Okay? Starting address is 0000H. Ending address is FFFH, right? That is the minimum and maximum address range I have. Right? If I want to interface this directly to 8086, anytime, can I extract 16-bit data from here? Impossible, right? How can I do it? Two memory location at a time. How can I access in one machine cycle? It can give only at a time. It can give you only one 8-bit data, right? I've understood. So I can't do this. 8088 is okay. 8088 has 8-bit data bus. This also 8-bit data bus. Okay. But 8086 has 16-bit data bus. But this is only 8-bit data bus. So at a time, this can give only 8-bit data, but this can take how many data? 16-bit data. So definitely we have to go for different arrangement, right? So what we do here is, just try to understand, it's very simple. What we do here in this case is, instead of using 1 megabyte chip, what we do here is, listen carefully, we use two memory chips of size 512 kilobytes and another 512 kilobytes. This can give you 8-bit data, right? Memory byte addressable. This can also give another 8-bit data, right? What size? This is 512, this is 512. Now I will design this memory in such a way that your first address 0000H will be in this memory. Your another address, that is odd address 0001 will be in this location. 00002 will be here. Okay? 00003 will be here. 00004 will be here. 00005 will be here. So what I have done, my entire address range of 1 megabyte, which is 000H to F, I have divided into two banks. Okay, two banks, each of size 512 and 512. This will hold the even address part of this range, this will hold odd address of part of this. I understood this. Okay. Now can you tell me what is the last address of this? This is F. Yes or no? What is the last address of this? Last address of this. Exactly. F, E. Now totally it is 1 megabyte. Yes or no? Your total memory is 1 megabyte. No doubt about it. But we are dividing it into even memory bank, even address memory bank, and odd address memory bank. What is the purpose of doing this? So that whenever you want to read 16-bit data, it will read at a time one from even address and then from odd address. Right? Now suppose what is the address you want to read? Now let us take the previous example. This example, okay? 4378, okay? 4378, okay? Now 437A is the offset address, right? 437A is the offset address, right? How do you get the 16-bit physical address for this? Suppose your data segment is 2000. It will be 20000H plus 437A, right? 437A. It is 2437A. Right? So what is the next address? 2437B. Now suppose you are having your one address is 2437A. Where will be 2437B? It will be in the another memory bank. 2437B. Right? This will be having your BL. This will be having your BH. So when microprocessor execute the instruction move 437A, BX. BX is 16-bit content, right? 16-bit content. So what microprocessor will do? At a time in one machine cycle, it will take lower byte from 2437A from this memory bank, higher byte from 2437B from another memory bank. At a time it will take. It will take 8-bit from here, BL from here, and BH from here. This is the way we divide the memory map. We divide the memory, and this is called as even memory bank, even address memory bank. This is called as odd address memory bank. Right? Have you understood now? Okay. This is the way we design our memory for 8086 microprocessor. Right? Now, let us see. That's what I have explained you. I have already explained you what is odd bank and what is even bank. Okay? See here. I have already explained you about this. Your entire memory, right? Your entire memory is divided into two memory banks. See, this is for 8088. You have understood this? For 8088, do you require to divide it even in our memory? Not required, right? Because it's 8-bit, microprocessor is also 8-bit, your memory is also 8-bit. Not required. Right? Now what we do in 8086 is, listen carefully, we are dividing entire memory. Suppose if 1 megabyte is a capacity, into two 512 KB of memory chip. So one memory chip will hold only even address, okay? Another chip will hold only odd address.
So why is it both have A1 to A90?
Where?
In the 8086, both having A1 to A90.
Both require, right?
Oh, that's address. Okay, yeah.
Both require 20-bit address.
The
Right.
data was to be.
Now see here, just try to understand why only A1 to A19. A0 is used to separate, select your even bank and odd bank. To address 512 kilobytes, how many address lines are required for you? this chip size is 512 kilobytes. Does it require A0 to A19 address line? How much it required? One less, right? That's why you have A1 to A19 here. Have you understood now? Right? See, this is 1 megabyte. This requires A0 to A19. Same thing for 8086, we are trying to divide into one even memory bank, odd memory bank. But if you combine this, totally it is 1 megabyte only. Right? If you look at this combination, it is 1 megabyte only. But so as to get both higher and lower order data, 16-bit data at a time in one machine cycle, you are trying to divide it into even memory bank and odd memory bank. Which signal differentiates? How do you select this chip and this chip? Depending on your A0 bit. Right? Can you check every even address, your A0 will be 0, yes or no? Can you just imagine? Every even address. What about A0 bit? Always 0, right? Always 0. That's why whenever A0 is 0, this particular memory chip is selected. That's why it is connected to chip select. Now, see here. Bus high enable. You must have seen in the pins and signals. Okay. Whenever microprocessor need to copy the higher order address bus, okay, higher order data bus high enable will go low. Okay, at that time your bus high enable chip will become low. So what will do microprocessor? At that time it will access the data from the odd memory bank. Have you understood this? Right? Okay. So in microprocessor for 8086, you divide entire memory into odd and even memory bank. Okay, this is what required whenever you design a memory system. In 8088, while dividing the entire memory map, okay, you are not divided into even and odd memory, right? But here you have to do. Okay, so listen carefully about the design. So have you understood this concept? This is very important. Okay, now let us go to an example. Now, it's very important. Now tell me, which are those two pins will select either even memory bank and odd memory bank? You have divided the entire memory, 1 megabyte of memory, into two memory banks, right? One is even memory bank and the other is odd memory bank. Right? Of course, whenever microprocessor generates odd address, data should be taken from the odd memory bank, right? Whenever microprocessor generates even address, it has to be taken from even address. There should be some signal which selects this chip, right? That is nothing but your A0 and bus I. Okay, now see, this table is very important. What happens? How does microprocessor gets the data? Okay, whenever the bits on bus I enable and A0. See here, when bus I enable is 0, see, and A0, both are 0. Okay, that means microprocessor has to select both even and odd memory bank. Yes or no? Both are low, right? Okay, in the previous even and odd memory bank division, we have seen, right? Right? So it is active low. A0 is active low, bus I enable also active low. So when A0 is low and bus I enable also low, definitely all 16-bit content will go, right? Have you understood now? Right? All 16-bit content will go. See, your microprocessor instruction need not be always 16-bit. Right? See, your microprocessor instruction, in this case, it is 4374, BX. It need not be that. It can be move 4374, BL. Yes or no? When the instruction is 16-bit right, it has to read 16-bit data. But in the second instruction, does it have to read 16-bit data? No, right? At that time, you don't want both A0 and bus I enable to be 0. Right? In this case, it will read whole world. This is word. It will read whole world, but this will read only byte, byte, byte. Right? That's why we have this. When A0 is 0, bus I enable is high, it will read or write whole word. Now see here. Now you just imagine when bus I enable is low, A0 is 1, can you tell me what it will read? It will read or write only higher byte, higher byte, higher byte. Okay. Now this is 1, this is 0. It will read only lower byte. Now tell me what happens, both are 1? It is active low, right? Nothing will happen. I have understood this. Now you understood how this bus I enable and A0 controls reading word or reading byte. Right? Now let us go to design. You can just check what happens to the bus cycle. Okay. Suppose your address is 0000. Okay. Address is 0000. Data type is byte. Okay. Data type is byte. Bus I enable is 0. Okay. A0 is 0. In one bus cycle. In one bus cycle. You know what is bus cycle, right? In one bus cycle, the data line D0 to D7 brings in the data. It will brings in lower byte data, yes or no? Because A0 is 0, right? Now, see, address is 0000. Now see here, word, you are supposed to take the word, see here, bus high enable is 0, A0 is also 0. That means in one bus cycle, how much data it will take? It will take entire data in D0 to D15 data bus. Fine. Okay. Now let us see this. Suppose your address is 0001. Address is 001 now. Okay. Have understood this. Address is 001. It's an odd address, right? And data is of byte. Bus I enable is 0. A0 is 1. In one bus cycle, what it will read? Higher order data. That is, it will read only in D8 to D15. Huh? Okay. It will read only through D8 to D15. Now, see here. Suppose, see, there may be possibility that sometimes when you give address, okay, you may have address 0001. Supposed to be it is actually odd address, right? Now suppose your bus high enable is 0 and data you want to read is word. Data you want to read is word, right? So it will take 2 memory cycle. It will take 2 cycles to read the data, right? Example I will tell you. Suppose move, if you just give move, in the bracket I have 0001. Okay? Try to understand this. Move in the bracket I will use 0001, comma bx. Right? Bx. Always we said that your lower order will go to the even address, higher order will go to the odd address, right? Yes or no? But in this case, what happens? Tell me. Suppose you are having your data segment is 0000. Suppose data segment is 0000. What is the effective address? Effective address is 00001, right? So in 0001, actually what it should go? Here. Actually, as per the statement, BL should go here, right? And in 00002, right? What should go? BH will go. See, this is a conflict, yes or no? As per our design rules, your all the even address will hold lower byte, right? Understood, right? But your odd address should hold the higher byte. But here it is ulta. Right? In such case, it will not do the transfer in one machine cycle. It will take two bus cycle. See here. Address is 0001. Data you want to transfer is word BX 16-bit data. What it will do? It will make bus I enable 0 and A01 in first cycle. In first cycle, it will take D8 to D15. See here. First, in such case, it will take higher order data first. Okay, it will take higher order data first. Okay, it will take higher order data first. Then in the next cycle, it will make bus I enable 1, A00. Next cycle, it will put the data in even address, lower order byte. And this happens only when your address is odd. Whatever address given here is odd. Have you understood? Right? If it is 0000, can you tell me which option it takes? If I give move 0000, comma bx, which option it takes? It takes this option. But if I give 0001, but in this option, it will take only one bus cycle. But in this option, it will take two bus cycles.
Sir, so now where is it stored? Which part is stored?
Which?
The lower part of this.
It will be stored in the respective even address only. Suppose in this case, see here.
No, so in the above example, the one you wrote.
This, whatever you wrote, okay, this is supposed to go to odd part, right? It will go and sit in odd only, say D8 to D50.
So lower part will be above 0.
Exactly. In this case, it will happen. All odd address will be stored there itself. That means it is supposed to be stored in the even address, right? But it will stored in the odd address. But at what cost? 2 cycles. That's why, have you seen whenever you try to do debug in the lab, the address will be generated by the compiler itself. All the memory addresses, when you have executed the program in the lab, right? All the addresses are automatically done allotted by the memory itself. Even though you have used org, it didn't work, right? Have you observed it? Why? Because your compiler will do memory allocation, address allocation in such a way that whenever you want to have a word access, it will try to do it in one bus cycle only. It won't create any situation that you have an address something like this, okay, and try to transfer the data. Right? Okay. So this is about how 8086 microprocessor transfers the data. Okay. So